This is the third lecture of a planned 6-part lecture series on the strategic bombing campaign of Japan. The fourth lecture will be about the race with the Nazis to build the bomb. The fifth lecture will be about the monumental American effort to build the bomb called the Manhattan Project. The final lecture will be about the 2 atomic missions over Hiroshima and Nagasaki. To better understand what happens during a nuclear explosion and the awesome power released from such an explosion, I first want to review a bit of nuclear physics that results in the explosion. That is the topic of this lecture. The atom is composed of 2 major components, the nucleus and the electron. The nucleus is composed of protons and neutrons. The proton has a positive charge and the neutron has no charge. The electron has a negative charge. In a neutral state, the number of electrons is the same as the number of protons. The number of protons determines the atomic number. In the case of hydrogen, there is only 1 proton and only 1 electron, hence its atomic number is 1. Uranium has 92 protons and electrons, hence its atomic number is 92. The atomic weight of an atom in a neutral state is the sum of the protons and neutrons, the weight of the nucleus. The number of protons for a given type of atom never changes. Uranium always has 92 protons. The number of neutrons, however, can change. 2 atoms with the same number of protons but different numbers of neutrons are called isotopes. The number of neutrons determines the isotope of the atom. Uranium-235 has 143 neutrons. Uranium-238 has 146 neutrons. The 3 isotopes of uranium, 234, 235, and 238, all have 92 protons in their nuclei and 92 electrons in orbit around the nucleus. But uranium-238, which accounts for more than 99% of natural uranium, has 146 neutrons in its nucleus, compared with 143 neutrons in the rare uranium-235, which accounts for less than 0.7% of natural uranium. The even rarer isotope of uranium-234 has 142 neutrons and is found only in trace amounts of natural uranium. Before I go any further, I need to define a process essential to our understanding of what happens during a nuclear explosion. Nuclear fission is the splitting of the nucleus of an atom into nuclei of lighter atoms, accompanied by the release of energy. In the 1930s, scientists learned a lot about the structure of the atom by bombarding it with subatomic particles. Ernst Lawrence cyclotron at UC Berkeley and the Van de Graaff generator developed by Robert Van de Graaff at Princeton were particle accelerators designed to bombard the nuclei of various elements to split the atom. Attempts of the early 1930s to split the atom required huge amounts of energy because the first accelerators used protons. Not surprising, Ernest Rutherford, Albert Einstein, and Niels Bohr regarded particle bombardment as useful in furthering the knowledge of nuclear physics, but otherwise had no practical application in the foreseeable future. Niels Bohr, the Danish Nobel laureate, agreed that the chances of taming atomic energy were remote. I need to get this concept out before we go any further because it is important to understanding what happens during a nuclear explosion. In 1905, Albert Einstein formulated his famous equation, E equals mc squared, as part of his theory of relativity. Essentially, what this equation says is that mass and energy are equivalent. I'll come back to this in a few minutes. In 1934, the Italian physicist Enrico Fermi began bombarding elements with neutrons rather than protons. He paid little attention to the possibility that matter might disappear during bombardment and result in the release of huge amounts of energy. During his studies of nuclear fission, Fermi and his colleagues found that carbon proved useful as moderators in slowing the bombarding neutrons and that slow neutrons produced the best results. One element Fermi bombarded with slow neutrons was uranium, the heaviest of the known elements. There was disagreement over what Fermi had produced in this reaction. Some thought the resulting products were transuranic elements, while others noted that the chemical properties of the fission products resembled those of lighter elements. Fermi himself was unsure. For the next several years, attempts to identify these products dominated the research agenda in the international scientific community. The answer came out of Nazi Germany in December 1938. The transuranic elements are the elements with atomic number greater than 92, which is the atomic number of uranium. All of them are radioactively unstable and decay into other elements. With the exception of neptunium and plutonium, which have been found in trace amounts in nature, none occur naturally on Earth. They are synthetic elements. The nuclear age was born on December 17, 1938, when the German chemist Otto Hahn and his assistant, Fritz Strassmann, working at the Kaiser Wilhelm Institute for Chemistry in Berlin, published the results of their experiments, bombarding uranium atoms with slow neutrons. The Nazis were the first off the blocks in obtaining an atomic bomb. Hahn and Strassmann reported their findings by mail to Lisa Meitner in Sweden, who had, a few months earlier, fled Nazi Germany. Meitner and her nephew, Otto Frisch, theorized and then proved that the uranium nucleus had been split and published their findings in Nature. By analogy with the division of biological cells, Frisch named the process fission. When Hahn and Strassmann bombarded uranium with neutrons in their lab in Berlin, they made an unexpected discovery. The uranium nuclei broke into two pieces. They split not into the new transuranic elements that some thought Fermi had discovered, but into two lighter elements. In this example, the uranium was split into the known elements of barium and krypton. Another of their discoveries was that the sum of the masses of the fission products, barium and krypton, was less than the mass of the original uranium nucleus. What happened to this other mass? Where did it go? The total mass of the products of nuclear fission is less than the mass of the original nucleus. This difference is known as the mass defect. It is equivalent to the binding energy of the nucleus. It followed from Einstein's equation, E equals mc squared, that the loss of the mass resulting from the splitting process must have been converted into energy in the form of kinetic energy that in turn could be converted into heat. Let's look a bit more closely at the nucleus and what happens when the atom is split during fission. As mentioned previously, a nucleus is made of positively charged protons and neutral neutrons. The positively charged protons repel each other. Like charges repel, and opposite charges attract. In spite of the tendency of the protons to repel each other, how then do they stay bound together in the nucleus? Why do they not push away from each other? It takes energy, called the binding energy, to hold them together within the nucleus. Here is the chemical equation that describes what happens when an atom of uranium-235 is split during fission. The uranium nucleus absorbs a neutron, which results in the nucleus splitting into two different, lighter nuclei, in this case one barium and one krypton nucleus plus three neutrons. These three neutrons are now free to hit and split other uranium nuclei. Notice also that there is something else that is released during this reaction, Q. Here is a pictorial representation of what happens to the nucleus during fission. From the left, a neutron collides with the uranium-235 nucleus with the result that the uranium nucleus is split into two lighter nuclei and three neutrons. As in the arithmetic equation in the previous slide, there is also Q energy generated with each nuclear fission. A nuclear chain reaction occurs when a single nuclear reaction causes an average of one or more subsequent nuclear reactions, thus leading to the possibility of a self-propagating series of these reactions. This occurs when a heavy isotope, such as uranium-235, is split in a fission reaction. The fission reaction produces free neutrons, which can split another uranium nucleus, which produces more free neutrons. The reaction continues in a self-sustaining process. The critical mass is the smallest amount of a fissionable isotope or fissile material needed for a sustained nuclear chain reaction. During fission, some neutrons collide with another uranium nucleus, initiating another fission as part of a chain reaction. Other neutrons are lost and do not participate in further fission reactions. A subcritical mass is a mass that does not have the ability to sustain a fission chain reaction. When a nuclear chain reaction in a mass of fissile material is self-sustaining, the mass is said to be in a critical state. The rate of neutron loss is equal to the rate of neutron creation by fission. A supercritical mass is a mass which, once fission has started, will proceed as a chain reaction at an increasing rate. To achieve a nuclear explosion, two subcritical masses of uranium or plutonium must be kept separate until the moment of detonation. In the case of uranium-235, a nuclear bomb starts with two physically separated subcritical masses of uranium. As soon as they are brought together, they form a supercritical mass which explodes. This is accomplished with a gun-type configuration. I will go into this in more detail in the lecture on the Manhattan Project, Lecture 5 of this series. In the case of plutonium-239, a hollow sphere of plutonium is rapidly compressed by conventional explosives. This leads to a concentration of plutonium in the center that is greater than the critical mass necessary for a nuclear explosion. Again, I will go into this in more detail in the lecture on the Manhattan Project. The important thing to understand here is that for a nuclear explosion to take place, two subcritical masses must be kept separated until the moment of detonation, when they are forcibly and rapidly brought together to form a supercritical mass that can sustain a chain reaction. A controlled self-sustaining reaction can make it possible to generate a large amount of energy for heat and power, while an unchecked reaction could create an explosion of huge force. To build a bomb, the physicist had to answer two fundamental questions: how much fissile material would be required for the weapon, and how much time would be needed for an effective detonation. They wanted a 20-kiloton explosion. How big is a 20-kiloton explosion? A 20-kiloton bomb is equivalent to 20,000 tons of TNT, which is the same as 40 million pounds of TNT. That's a big bomb. A fully loaded B-29 could carry 10 tons of bombs. Each of these planes represents 100 B-29s. So one 20-kiloton bomb is the equivalent of a 2,000 B-29 bomber raid. To achieve a 20-kiloton explosion required just 10 kilograms of uranium-235. We now know that we need 10 kilograms of uranium-235 to get a 20-kiloton explosion. How much time will it take during the detonation to achieve this result? Using very fancy calculations, it was determined that 80 generations of fission reactions was needed to get a 20-kiloton explosion. How big is 80 generations of fission reactions? It's equal to 1.2 times 10 to the 24th power. How big is that number? It's 12 with 23 zeros after it. That's a big number. I don't even know what this number is called. And remember, there is a little bit of energy Q that is generated with each fission reaction. Even if Q is small, when multiplied times this big number, it's a lot of energy. How much time does it take for 80 generations to take place? Don't get bogged down in the math. During fission, a neutron travels 10 million meters per second. At this speed, one generation of fission will take 100 millionth of a second. So 80 generations will take place in just under 1 microsecond, or a millionth of a second. The exponential growth of neutrons means that the last 10 generations produce approximately 99.9% of the energy in the explosion. Thus, it is important to keep the supercritical mass together long enough to release the desired amount of energy, otherwise, it is a dud. This means that the two subcritical masses must be brought together very quickly. While researching uranium fission, a new element was discovered that was named plutonium after the planet Pluto. Plutonium has 94 protons, its atomic number, and 239 protons and neutrons, its atomic weight. Plutonium was found to be twice as fissionable as uranium-235 and, as was later discovered, would produce a more powerful bomb than the uranium bomb. Plutonium was produced by irradiating uranium in a nuclear reactor. A neutron released by the fissioning of a chain-reacting U-235 nucleus is absorbed by the nucleus of U-238. The resulting U-239 nucleus decays with a half-life of 24 minutes into neptunium, which in turn decays to plutonium-239 in approximately 3 days. Each decay is accompanied by the emission of an electron. Now that we have a basic understanding of what occurs during a nuclear explosion, in the next lecture I will discuss the race between the Allies and Nazi Germany to be the first to build the bomb.